Let's explore doubly linked lists, which are a powerful data structure. Doubly linked lists are a dynamic data structure where each node contains data, a reference to the next node, and a reference to the previous node. This structure allows for efficient traversal in both directions. Now let's discuss the advantages of using doubly linked lists. They allow bidirectional traversal, meaning you can navigate both forward and backward through the list. Deletion becomes easier, as there is no need to traverse from the head to find the previous node. They can be used to implement data structures like double-ended queues or deques efficiently. They also provide quick insertion and deletion at any position, which can be done in order one time. Here's a comparison with singly linked lists. In a singly linked list, you can only move in one direction, whereas in a doubly linked list, you can move in both directions. Now let's dive into the structure of a doubly linked list node. Each node contains a previous pointer, which points to the previous node in the list. It also holds the actual data that the node stores and a next pointer, which points to the next node in the list. Here's a basic Python implementation of a node. First, we define a class called node. The constructor initializes the node with the provided data, sets the previous pointer to none, and sets the next pointer to none. Let's see how to implement a doubly linked list in Python. We define a class called Doubly Linked List. The constructor initializes an empty list by setting the head and tail to none and initializing the size to 0. The isEmpty method checks whether the list is empty by verifying if the head is none. The length method returns the number of elements in the list, which is stored in the size variable. Now let's explore insertion operations in a doubly linked list. There are three main ways to insert a node. You can insert at the beginning, where the new node becomes the head of the list, with its next pointing to the old head. You can insert at the end, where the new node becomes the tail of the list, with its previous pointing to the old tail. Finally, you can insert at a specific position, where the new node is inserted between two existing nodes, with proper previous and next pointers set. Here's how to insert at the beginning. First, create a new node with the given data. If the list is empty, set both head and tail to the new node. Otherwise, link the new node with the current head, update the current head's previous pointer to the new node, and update the head to the new node. Finally, increment the size of the list. Now let's look at how to insert a node at the end of a doubly linked list. Here's a visualization of the process. There's an original list and a new node which will be added at the end of the list. These are the steps to insert at the end. First, create a new node with the given data. Set the new node's previous pointer to the current tail. Set the current tail's next pointer to the new node. Finally, update the tail to point to the new node. Here's the code to insert at the end. First, create a new node with the given data. If the list is empty, set both head and tail to the new node. Otherwise, link the new node with the current tail, update the current tail's next pointer to the new node, and update the tail to the new node. Finally, increment the size of the list. Now let's explore how to insert a node at a specific position in a doubly linked list. This visualization shows the insertion of a new node between node 2 and node 3. Here's the code to insert at a specific position. First, handle the special cases. If the position is less than or equal to 0, insert at the beginning. If the position is greater than or equal to the size of the list, insert at the end. Then create a new node with the given data, find the node at the specified position, and update the next and previous pointers of the new node and the adjacent nodes. Finally, increment the size of the list. Now let's explore deletion operations in a doubly linked list. There are three main ways to delete a node. You can delete from the beginning, which removes the head node and updates the head to the next node. You can delete from the end, which removes the tail node and updates the tail to the previous node. Finally, you can delete from a specific position, which removes a node at a specific position and reconnects the adjacent nodes. A significant advantage in a doubly linked list is that direct access to the previous node makes deletion easier compared to a singly linked list. This visualization illustrates the process of deleting node 2, and then the new connections being formed after the deletion. Let's look at how to delete a node from the beginning of a doubly linked list. This is the visualization of the process, showing the list before and after deletion. Here are the steps for deleting from the beginning. Save a reference to the current head node. Update the head to point to the next node. Set the new head's previous pointer to null. Finally, delete the old head node. Here's the code. First, check if the list is empty. If it is, return none. Save the data from the head node. If there is only one node in the list, set both head and tail to none. Otherwise, move the head to the next node and set the previous pointer of the new head to none. Finally, decrement the size of the list and return the data that was deleted. Let's summarize the key aspects of doubly linked lists. The key advantages are bidirectional traversal, efficient deletion operations, easy implementation of data structures like deques, and order 1 insertion and deletion at both ends. The time complexity for access and search operations is order n. Insertion and deletion at the beginning and end take order 1 time, while insertion at a specific position takes order n time. The limitations are higher memory usage than singly linked lists and a more complex implementation. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.